Hi, everybody. In this lecture, I'd like to talk to you about equipotential surfaces and point charges. So what is an equipotential? Well, if you look here at the drawing, it shows you an electric field E, indicated by the orange arrows, and it's nice and uniform and straight and the same everywhere. And that electric field is pointing to the right. And then we see a particle indicated by this little black dot that moves through some displacement or motion, and the vector displacement is called S. So it could, when it moves through this path, go straight from A to B, or it could take some other random path, such as moving from A to C and then from C to B. And either way, it ends up at the same value of the electric field, because the electric field, since it's uniform, is going to be shown here, okay? Now, points B and C are at the same potential energy. Remember that we said that if it's moving through the displacement, that the change in potential energy is minus QED times cosine of theta, okay? Now, since it's taken that cosine of the angle theta, if it moves from A to B or A to C, the cosine of theta bit will cancel out any part of that displacement that's not parallel to the electric field. That's what the cosine of theta does. It's the projection of the displacement and the electric field vectors onto one another. Now, if that's really complicated, you don't have to remember it, but just remember that if you draw a line or a plane that's perpendicular to the electric field lines everywhere, that those points will all be at the same electric potential energy or voltage, as it turns out. And we call those equipotential surfaces, okay? So an equipotential surface is all points in a plane perpendicular to the uniform electric field or to an electric field, and they're going to be at the same electric potential energy. So this is what it's like for an electric field that's uniform, straight, and pointing in one direction. Your equipotential surfaces are basically flat planes, and you can envision a flat plane that connects line B to C, but then sticks out of the screen at you coming that way. Okay, so you can picture that. Now, if you have instead a situation where the electric field isn't uniform, like for example, for a point charge, we know that for a positive point source charge, the electric field points radially outward, as is shown here by these orange arrows, okay? In that case, your equipotential surfaces are still going to be perpendicular to the field at all points. But now you can see that those don't make up planes, but rather spheres that are sort of like nested Russian dolls around your point charge. In other words, everything that's the same radial distance away from the point charge makes up a sphere that encloses the point charge, and that sphere is an equipotential surface, right? So here, these blue dashed equipotential lines everywhere are perpendicular to your field lines, and so you know those are equipotential surfaces. So that's interesting to think about. Okay. Let's talk about point charges a little bit more. Let's figure out what the voltage equation is for a point charge, okay? If they're really at the same electric potential energy, for example, those spheres that nest the charge, then they'd also be at the same voltage, because remember that, you know, delta U is equal to Q delta V. So they're related to one another by just a constant. So let's figure out the equation for the voltage here. If you're moving from position A to position B, for example, then you're going to move through a voltage difference or a voltage change of KQ, Coulomb's constant K, which is 8.99 times 10 to the 9th in SI units, times whatever your charge is that created your field lines or your voltage. KQ times 1 over RB minus 1 over RA. So that gives you the voltage difference in between a point that is a radial distance RA away from the charge and a radial distance RB away from the charge. Now, the voltage is actually going to be independent. That change in voltage between A and B is independent of the path that you use to get to points A and B. It doesn't matter whether you go straight radially outward or take some windy path to get in between those 2 points. The voltage difference between the 2 points is the same. It's also customary to choose a reference or a ground for point charge problems where the voltage is 0, when you get infinitely far away from the charge. And that kind of makes sense. If you're infinitely far away from a charge, it's not really influencing what's going on around it too much, right? And so you would have a voltage of 0 if you were infinitely far away from a single positive point charge. So if you do that, then the voltage for some point at for some distance r from a charge q would be V is equal to kq over r, and that would give you the voltage at a distance r radially away from a charge q, and remember k is that Coulomb constant, 8.99 times 10 to the 9th. Now, if you drew that, what would it look like? So it would look like this. This gets cut off because you can't graph infinity. But here you are. This is a plot of the electric potential or voltage on the vertical axis is in this 3D visualization. And you can see that the voltage is going to go to infinity as you get super duper close to the charge where r shrinks to 0. And you've got that 1 over r dependence of the voltage as you move away from the point. Okay. Now, we talked about dipoles briefly, but I'm not sure if we defined them very carefully. So let me go ahead and remind you or define the fact that an electric dipole is a positive and a negative charge that's equal in magnitude and separated by some distance, usually a pretty small distance. Here. So this is a picture of what the electric field lines would look like, but for an electric dipole, and we talked about that in a previous lecture. And then up here is the picture of what the voltage would look like for an electric dipole. Remember that voltage for a point charge is kq over r, right? And so if you have a positive charge, then as you get infinitely close to that charge, your voltage goes to positive infinity, as is shown here. But if you have a negative charge, then as you get infinitely close to or get close to r equals to 0 for that negative charge, your voltage goes to minus infinity because Q is negative. So that's what is shown here. So you can see here what that voltage for a dipole would look like. And you can see that because there's a really steep slope of your voltage in between your positive and negative charge, that indicates that you're going to have a really strong electric field in that region. Now, if you have a bunch of point charges, we talked about a dipole, but let's talk about if you have a whole bunch of charges, then you can find the voltage due to many point charges just by summing up the voltage due to each individual charge. This is another example of the superposition principle. In this case, it's easier, though, than it is with electric fields because voltage is a scalar. So you just straight up sum the numbers, right, to get the total voltage. So the sum is the algebraic sum, and it's V is equal to the Coulomb constant times the sum over all the charges of Qi over Ri. Okay, and you just keep summing. And this assumes that the voltage goes to 0 as you get infinitely far away from the collection of charges. So if you see a problem that says, assume that the potential or the voltage is 0 relative to infinity, then that's what that assumption means. And of course, that makes perfect sense because, 1 over 10 is 1/10, right? 1 over 100 is 0.01, 1 over 1,000 is 0.001. So as the value of R gets larger, your voltage gets smaller and smaller until it reaches 0 when R is infinity. Okay, now, remember, your voltage is a scalar. Your voltage is directly related to your potential energy. And just like any other potential energy, you're comparing that value to a reference point. For voltage, that reference point is called the ground, right? That's what we call it in electrical terminology a lot of times. So if you see that term, that's what that means. Ground for point charges is at infinity, okay? Because of the kq over r, and as r goes to infinity, V goes to 0. But ground doesn't always have to be infinitely far away. It does depend on the problem. Like, for example, for this battery, the ground is at the bottom or negative terminal of the battery, and it's plus 1.5 volts compared to the back side of the battery, if that makes sense. So it's not always going to be at infinity. It depends on the problem. But for point charges, infinity is a convenient ground. Let's do an example problem of finding the voltage for multiple point charges. In this case, we have 4 plus 6 microcoulomb point charges at the corners of a square that's 2 meters on a side. And then the question asks, What's the electric potential of these charges relative to infinity at the center of the square? So just to remind you, electric potential, that means voltage. They're synonyms. I just use voltage most often because I find it less confusing for students. But you will see questions that say electric potential, and what that means is voltage, okay? All right, so if the square is 2 meters on the side, I have a little graphic here. You want to know what the voltage is at X marks the spot at this yellow X here that I put in the center. And if the square is 2 meters on the side, what you need to know is the distance from each one of those charges to the center of the square. Well, if it's 2 meters on a side, then you can drop a little perpendicular line from your X marks the spot to the bottom of the square, and you're going to have a triangle, which has a right triangle, which has legs of 1 meter for the straight sides, and then for the hypotenuse, the length of that will be the square root of 2. And that's because you can use the Pythagorean theorem to figure out the length of the hypotenuse of a right triangle. And remember that a squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse. So 1 squared plus 1 squared is 2. And then if you take the square root of that, then that gives you c. So that would be root 2. So the distance from each one of these charges to the center of the square is root 2 meters. Okay, so what we can do is we can just find the voltage. Since all of these charges are exactly the same, it makes it pretty easy. We can find the voltage due to one charge and then just multiply that times 4, and we're done. Okay, so V is equal to KQ over R. K is 8.99 times 10 to the 9th in SI units. Q is 6 microcoulombs, which remember micro is 10 to the minus 6. So that's times 6 times 10 to the minus 6 coulombs. And then you just divide by R, which is the distance from the charge to the point in question. And R is the square root of 2. So when you plug all that into your calculator, you get 38,000 volts or 38 kilovolts. Remember, this is the SI prefix for kilo, and kilo means 10 to the 3. So this is 38,000 volts or 38 kilovolts. And then to find the total voltage, you would just multiply the voltage for one charge by 4, because there's 4 charges. And so V total would be 4V1, which is 152,000 volts or 152 kilovolts. Okay, so that's how to do that. Okay. Now let's talk about the potential energy equation for point charges. So we talked about the equation for voltage, and remember that potential energy and voltage are related very simply, that U is equal to QV. So the voltage, remember, is just dependent upon the field. So basically, you're asking yourself, when you're asking the voltage due to a point charge, you're saying, what kind of electric field, how strong is the electric field that this point charge is establishing? What's that like? And you're putting it in terms of the scalar voltage instead of the field, right? So you just need one charge to establish a field and one charge to establish a voltage. But if you're talking about the potential energy, you're talking about the interaction of a charge field system. And so to do that, you have to multiply Q times V. So what you do is you have the potential energy between charges. So if you're talking about the electric potential energy, then you have to have at least 2 charges in order to find the potential energy for it. So for example, if you have 2 charges in blue and orange here, and they're Q1 and Q2, then the potential energy for that system is U is equal to K times Q1 times Q2 over the distance in between the 2 charges, which they've called here R12. Okay, and that's because you multiply Q times V, and remember that the voltage for a point charge is KQ over R, so you're just adding an extra charge in there, and there's your potential energy equation. I hope that makes sense. Now, if the 2 charges are the same sign, then KQ1, Q2 over R is going to be a positive value, because positive times positive is, of course, positive, and negative times negative is also positive. So that means that work must be done in order to bring those charges together. If the potential energy is positive, then you have to do work to get them together because they repel one another, right? Now, if the 2 charges have opposite sign, then that means that you have Q1 times Q2 giving you a negative number. So the potential energy is negative, and work has to be done to keep the charges apart because they attract one another. Remember, opposites attract. If you've got more than two charges, then what you can do to find the system's energy is find the potential energy for each pair of the charges and then add up all the pairs. So for three charges, for example, you'd have to find the potential energy between charge 1 and charge 2, and the potential energy in between charge 1 and charge 3, and the potential energy in between charge 2 and charge 3, and then sum them all up. KQ1, Q2 over R12 plus KQ1, Q3 over R13 plus Q2, Q3 over R23. Do that sum. And this is, of course, going to be the same no matter what order you add them in. So let's do an example problem for that to finish up. So show that the amount of work required to assemble 4 identical point charges of magnitude Q, so they all have the same magnitude, into a square with sides of length S, so this is S on all sides here, is 5.41 KQ squared over S. Okay, so this is a proof. We're proving that this is the answer. We're showing that it's true. Okay, so we've got to find the potential energy for this entire system, because remember, potential energy and the amount of work required to do something, they're equal in magnitude, okay? So we're going to sum up all the potential energies of all these pairs. So you have to count all the pairs. You don't want to count a pair twice. And sometimes if you have more than a couple, it's easy to list them out. So I listed out the pairs. I numbered the charges 1 to 4, starting in the lower left corner and going clockwise around the square. 1, 2, 3, 4, like that. Okay, so I've got 1, 2, 1, 3, 1, 4, and then pairs 2, 3, and 2, 4, and then pair 3, 4. And that's all the pairs. Now, I highlighted in yellow the pairs that have a distance S between them. So 1 and 2 have a distance S between them, right? And then 1 and 4 have a distance S between them. And then 3 and 4 have a distance S between them. And 2 and 3 have a distance S between them. So those all have been highlighted in yellow. But the pairs that are highlighted in blue are across the diagonal from one another. So 1 is across the diagonal from 3, and 2 is across the diagonal from 4, okay? And so the distance in between those pairs is S times the square root of 2, all right? There's 2 pairs that have that. All right, well, this makes it pretty easy, okay, because all the charges are the same, and then the distances are the same for 4 of them, and then a different distance, but it's the same different distance for 2 of them. So that makes the math pretty quick, right? We can just find the potential energy in between, for example, charge 1 and charge 2, and then we have 4 pairs that are going to have that same exact potential energy. So I can just multiply that times 4. So I've got 4 times K times Q squared over S, because remember, it's K, Q1, Q2 over the distance in between the pair, right? So the distance between the pair is S, that goes in the denominator. The charges are the same. Q1 times Q2 in this case is just big Q squared, and then times K. And then there's 4 pairs like that. So that's where that comes from. Now I have 2 pairs that are across the diagonal from one another. Remember that if you have a right triangle with sides S, you can use the Pythagorean theorem. And so this hypotenuse is going to be S times the square root of 2 for the distance in between 1 and 3, right? Because you have S squared plus S squared is 2S squared. And then you take the square root of 2S squared to get the length of that hypotenuse, which gives you S root 2. So I have 2 pairs, 1 and 3 and 2 and 4, right, that are across that diagonal from one another. So I have 2 for both pairs times K times Q squared over S root 2, the distance, right? Now, when I sum all that up, I can pull my KQ squared over S out because it appears in both terms. And then that is times 4 plus 2 over the square root of 2. And 4 plus 2 over the square root of 2, if you plug it into the calculator, is 5.41. So the potential energy, which would then be equal to the work to assemble the collection, is 5.41 times K times Q squared over S. All right, I hope that made sense. Hey, always remember when you're watching these online lectures that you can pause me, you can play me slower, you can stop and go back. That's one of the really nice things about having online lectures as compared to in-person lectures. I hope you understood all that. I hope it makes sense, and I'll see you next time.